Good morning students. In the last class we discussed about potential due to dipole and equipotential surface. So you know what is equipotential surface? The locus of all points having same potential is called equipotential surface. So we have studied the properties of equipotential surface. No two electric potential surfaces intersect each other. The electric lines of force are always normal to the conductor. No work is required to do work done to bring a charge from one point to another point in an equipotential surface. Now let us take some examples of equipotential surface. So for example, if you take a point charge, what is the Gaussian surface for this point charge? Is a spherical surface. So we can form concentric hollow spheres. See, the electric lines of force are moving in all directions. Now whatever the work done that is going to bring the charge from one point to another point is same. Okay, so like this, from where to where you bring the charge also the potential surface will be same. Similarly for these lines, what happens? These are the planes are passing through this equipotential surface. This is electric field. So these are the examples of what? Electric potential surfaces. The next important concept is potential energy. So what is potential energy? That we learnt in first year, that the energy possessed by a body, right? The energy possessed by a body due to virtue of its motion is called potential energy. Here the electrostatic potential energy is defined as, so here to bring one charge from infinity to a point we require to do some work done, right? So that work done is stored in the form of potential energy. If you want to form a system of charges, that energy required to form the system of charges is called potential energy. So we can define as, so what we can define? The electrostatic potential energy of a system of charges is defined as the work done in bringing the charges or assembling the system of charges by bringing them close together. Yes, so the electrostatic potential of a system of charges is defined as the work done in assembling the system of charges by bringing them close to each other from an infinite distance. Okay, so if you want to bring the system of, if you want to form a system, you have to bring charges from different places, and forming that system, the energy that is required is called electrostatic potential energy. If you want to write for one charge, what happens? It is defined nothing but what? The amount of work done to bring the charge against the electric field. So For one charge we can write as potential energy, that is electrostatic potential energy, is equals to work done against work done from infinity to r, that is equals to what ma? Infinity to r q into E. Is it right? So this is the formula for work done to bring a unit charge from infinity to r into distance. Is it right? Understood? Yes. Now we are going to derive a small, very important question of this chapter, 3 marks, that is potential energy of a dipole in a uniform electric field. Okay. Potential energy of a dipole in an uniform electric field. So what is potential energy of a dipole in an uniform electric field, right? See, let us take a uniform electric field. In this we place a dipole. You know the dipole is two equivalent opposite charges separated by a small distance. It is making an angle theta. Yes, okay. Now what is potential energy of a dipole is the amount of work done in rotating a dipole from perpendicular to an angle. So the amount of work done in rotating a dipole from any perpendicular to any direction in the presence of electric field is called what ma? Potential energy. The amount of work done in rotating a dipole from perpendicular to any given direction in an electric field is stored in the form of what? Potential energy, right? So amount of work done in rotating a dipole from perpendicular to any given direction against electric field, is stored in the form of what ma? Potential energy. Let, for example, small work done, let dW be the work done in rotating a dipole through an angle d theta. So we are consider rotational torque. So dW is equals to what is the torque acting on this one? Tau. We know already very well torque acting on a dipole. What is the formula? Tau is equals to what? P sin theta. Therefore dW is equals to what? P sin theta into d theta. So this is the work done in rotating a dipole through angle d theta in electric field. Now what is the condition? Total work done in rotating dipole from where to where ma? 90 degrees to theta. That is the condition, right? From perpendicular to any given direction. So integration of dW is equals to integration of 90 to theta P sin theta into d theta. As we know, integration of dw is what? W. P is constant, integration of sin theta into d theta, 90 to theta. What is integration of sin x into dx? Minus cos x. So minus, okay, let us keep like that, minus cos theta 90 to theta. That implies w is equals to, applying the limits, minus cos theta plus cos 90. Cos 90 how much? 0. So we can write as w is equals to what? Minus P cos theta. As we already said that this work done is stored in the form of potential energy. So U is equals to minus P cos theta. If theta is equals to 0, U is equals to what? Minus P, that is called what? When the dipole lies along the axis of electric field, it is in stable equilibrium. If theta is equals to 90, U is equals to 0, this is called what? 0 equilibrium. And if theta is equals to 180, U is equals to minus of minus plus, this is called what? Unstable equilibrium. So this is the complete derivation of potential energy of a dipole in a uniform electric field. In some cases, they will ask work done in rotating dipole from theta 1 to theta 2. Very important formula for problems point of view, that is equals to what? P into, instead of 90 to theta, what we will do? Theta 1 and theta 2. So what it becomes? Cos theta 1 minus cos theta 2. Okay, so this question is very important. See here, what is potential energy? The amount of work done in rotating a dipole from perpendicular to any given direction against electric field is stored in the form of potential energy. So let's assume that dw is the work done in rotating a dipole through an angle d theta. What is the work done? dw is equals to rotational force into angular displacement, tau into d theta. As we already derived in first lesson, torque acting on a dipole, tau is equals to P sin theta. Therefore dw is equals to what? P sin theta into d theta. Now what is the definition? Total work done in rotating dipole from 90 to theta. Integration of dw is equals to integration of 90 to theta, P sin theta into d theta. Integration of dw is w, P is constant. So what is the variable here? Angle. So P into integration of 90 to theta sin theta into d theta. W is equals to what? P. Integration of sin x into dx is what? Minus cos x. So minus cos theta 90 to theta. Applying the limits, minus cos theta plus cos 90. Cos 90 is 0. W is equals to minus P cos theta. This work done is stored in the form of what? Potential energy. Therefore U is equals to minus P cos theta. If theta equals to 0, U is equals to minus P, that is called stable equilibrium. If theta equals to 90, U is equals to 0, that is called 0 equilibrium. If theta is equals to 180, U is equals to P, that is called unstable equilibrium. Now what is the work done in rotating a dipole from theta 1 to theta 2? W is equals to P cos theta 1 into minus cos theta 2. Thank you, students.